Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Muqri Aqil bin Mazlan, a student in Master of Science in Electrical Engineering UiTM. Today I am going to present to you my current research progress, which entitled Deep Reinforcement Learning for 5G CV2X Ultra Reliable Low Latency Communication URLLC Data Management using Twin Delayed Deep Deterministic Policy Gradient TD3. This is the presentation outline. Start with the introduction, which is the background of study. Next is the status of major research milestones, and then the Gantt chart for the progress, followed by the status of publication and thesis writing, and last but not least, the planning for the next semester. CV2X is a state-of-the-art technology connecting vehicles to other technological units around it. It is the latest technology which will serve as a foundation for vehicles to communicate with each other and everything around it. CV2X enables the communication between vehicles, pedestrian, roadway infrastructure, and the network. CV2X includes the direct communication side link for V2V, V2I, and V2P by offering the extended communication range and reliability. Implementing CV2X can reduce to traffic congestion and enhance travel safety. CV2X application contributes to decrease the pollution by reducing the overall time spent on the road. The third generation partnership project, 3GPP, have been developing a cellular vehicle communication called CV2X, designed to operate over cellular networks such as 5G New Radio. 5G has three use cases. First is the Enhanced Mobile Broadband Communication, EMBB. Second is the Ultra Reliable Low Latency Communication, URLLC. And last, the Massive Machine Types Communication, MMTC. These use cases establish the requirements and building blocks for the 5G network. It is deployed to enable a high-speed mobile broadband to deliver extremely reliable low-latency communication and facilitate the mass deployment of low-powered IoT devices. GPP has established a standard for 5G new radio wave, which is established the expected level of performance for each slice, including measures such as quality of service, QoS, throughput, transmission rate, error rate ratio, and others. The network elements can support concurrent slice for diverse systems service system. Network slicing supports two main categories of services, URLLC and EMBB. URLLC requires low latency and high availability for applications like autonomous driving and utility grid protection. EMBB focuses on mobile broadband services for human-centric scenarios like accessing the multimedia content and data. As the demand for the mobile broadband continues to increase worldwide, there is need for enhanced mobile broadband services in order to address these requests. This expanded usage scenario would include new application area and criteria in addition to existing mobile broadband application while improving the efficiency and providing a more seamless user experience. In Figure 2 depicted the 5G network environment usage scenarios based on the aforementioned services. To be more specific, in 5G communication, the data rate for EMBB services must be maximized while satisfying the two conflicting requirements for the URLLC service, namely latency and reliability. For instance, the 5G NR system aims to efficiently support different types of autonomous vehicles with various usage scenarios within a single carrier bandwidth. To achieve this goal, the 5G NR system includes the new physical layer specification such as numerologies for the sub-carrier spacing and slot length, code block groups based on transmission, bandwidth path, and preemption-based URLLC scheduling. A preemption-based scheduling mechanism that enables immediate scheduling of URLLC traffic by puncturing or superimposing ongoing EMBB traffic. This preemption-based scheduling mechanism is also referred to as URLLC and EMBB dynamic multiplexing. Figure 3 depicts the resource allocation for EMBB user and the puncturing of resource block. The original blocks are assigned to EMBB user 1, user 2, user 3, and 4 respectively at the beginning of the slot. When URLLC traffic arrives at the base station, the data immediately scheduled by overwriting the part of ongoing EMBB transmission. These are the problem statement for this study. First, scheduling URLLC transmission is a major challenge for 5G and future wireless network. Multiplexing URLLC and EMBB on the space spectrum requires a suitable scheduling algorithm. Base stations require knowledge of the statistical channel model for optimal URLLC transmission. Conventional optimization techniques have been used for scheduling algorithms, but there are limitations due to the dynamic system states and feasibility. Second, the limitations of current deep reinforcement learning algorithm in addressing large and continuous action domains for scheduling decision in URLLC and EMBB coexisting scenarios while optimizing the system throughput and ensuring the URLLC reliability. This involves leveraging the EMBB resource allocation phase to schedule URLLC traffic and enhancing the DRL-based algorithm convergence. While existing DRL algorithm has shown promise in optimizing resource allocation and balancing trade-off between EMBB services queue length and URLLC services reliability, they are primarily effective in discrete and small action space. However, practical problems often involve large and continuous action domains, making the current DRS algorithm unsuitable. This research will focusing on the following three objectives. First, to investigate the current optimization techniques in scheduling of ultra-reliable low-latency communication and enhanced mobile broadband services on the same time frequency spectrum. Second, to develop a deep reinforcement learning model-free policy optimization scheduler for URLLC and EMBB services in 5G CV2X network under the continuous action space. Last but not least, to evaluate the performance of the proposed scheduler in terms of QoS parameters such as delay, jitter, and throughput. There are three questions that needs to be answered in this research. Question number one is how to design the dynamic scheduling mechanism to balance the latency and reliability requirements in the URLLC and EMBB coexisting services. Second question, what are the techniques that cater for learning in continuous action space in DRL model-free policy optimization that are suitable for scheduling of URLLC and EMBB services at the same time frequency spectrum in a 5G CV2X network? And the third question is, how does the performance of the twin delayed deep deterministic policy gradient TD3 scheduler compare to the existing scheduler in terms of QoS parameters such as delay, jitter, and throughput under the different traffic loads? The scope of these studies is as follows. The use of deep reinforcement learning framework with TD3 algorithm for URLLC data management. To learn the optimal resource allocation policy in real time by using the TD3 algorithm and network feedback. To utilize the neural network to model the queue function for dynamic resource allocation decisions. To conduct an extensive testing to assess the reliability, latency, and communication efficiency. It is based on a simulation and consider a single type of URLLC application. Reinforcement learning in massive access management for future wireless networks. Different distributed reinforcement learning frameworks to address the massive access management problem under the scale and resource constraint. Reinforcement learning is not effective in dealing with the high-dimensional input state space of complex and the large-scale future wireless network. Deep reinforcement learning combines the deep learning with reinforcement learning to learn from experience and solve the complex spectrum access decision-making tasks with large state space. The Markov decisions process is widely used decision-making model in DRL. It is a discrete time stochastic control process that can create a learning system where the agent models the decision-making problem in each learning step. DRL algorithm can be classified into off-policy and on-policy. Off-policy algorithm like learning use the epsilon greedy method for exploration and policy update. One limitation of policy algorithm is their long conversion time due to the variance between the Q values. Policy algorithms address this limitation by using the gradient update method for the policy revision during exploration. Policy optimization in DRL can generally be categorized into three main groups. First, the policy iteration methods, which alternating between the estimating the value function under the current policy and enhance the policy. Second, the policy gradient methods, which use the estimator of the gradient of the expected reward based on the sample trajectories and have a close relationship to policy iteration. And third, derivative-free optimization methods. These are the research methodology for this study. First, the literature review and background study be conducted to investigate the characteristics that affect the performance so that the network model can be developed. Next is the development of DRL model-free policy optimization scheduler for 5G CV2X network and the development of the simulation model where the algorithm can be implemented into the model and extract the performance parameters to be measured. After that, some performance study and model fine-tuning have been conducted to analyze the performance in terms of delay, jitter, and throughput. And then do some benchmarking on the DRL scheduler from the simulation. This is the summary of this study where the first problem statement is linked to the first objective and the second problem statement is split into two, which is the second objective and the third objective. The methodology have been conducted to achieve the outcomes. This is the current progress of this semester. As of date, we have selected policy gradient method as a reference to develop our model. Based on the current literature review, our initial proposed algorithm was based on TD3. However, in late 2023, a paper has been published in related research domains utilizing TD3. Consequently, we have revised our approach and proposed a new algorithm named Soft Actor Critic or SAC, which we believe surpasses TD3 in terms of performance. Both TD3 and SAC are end-of policy gradient algorithm. SAC is very efficient for energy-based optimization techniques due to the entropy factor regularization. TD3 works well with continuous action space but lacks the faster conversion rates. SAC incorporates entropy regularization, promoting diverse action exploration, which can be beneficial in complex environments. While TD3 employs deterministic policy, which might limit exploration in certain scenarios where stochastic policies are more effective. SAC is generally considered less sensitive to hyperparameter choice than TD3, simplifying the tuning process. And TD3 can be more sensitive to hyperparameter choices, requiring careful tuning for optimal performance. Next is the development of simulation model. A network topology for the implementation of the model has been devised by using OMNET as the discrete event network simulator, SUMO to emulate the real road traffic condition, PyBind to communicate between C++ and Python, and SIMO5G as the framework to simulate 5G network. Socket.io is a JavaScript library that enables real-time bidirectional communication between the web clients and servers. On the other hand, PyBind is a Python library that provides tools for binding C++ code to Python. It allows developers to write C++ code that can be called from Python, enabling the integration of C++ library into Python application. The OMNET simulation environment, which is built on C++, can be integrated with the DRL written in Python by employing the PyBind to establish seamless communication between the two programming languages. In the first phase, after completing the simulation, we derive the preliminary result that encompass the performance metric of data traffic via SIMO5G in the OMNET simulation. We utilize the existing internal scheduler as depicted in Figure 8. In the Figure 9 and 10 depicted the bar chart for the throughput and the delay of the schedulers. In the second phase, we integrate Python through the PyBind protocol to employ the external scheduler. This integration facilitates the use of external scheduler for the SIMU 5G framework in Omnet environment. In the third phase, we pursue to incorporating the DRL algorithm methods into the existing setup, thus enabling the simulation to benefit from advanced learning algorithms for scheduler optimization and management. One limitation of Omnet is that it uses C++ for simulation development. However, many DRL's algorithms are written in Python. We chose to use Python as a medium. This decision was driven by the fact that Python makes it easier for benchmarking purposes. The following is a Gantt chart for the study. Currently, the study is in the second semester where the development of the simulation model for the DRL algorithm. The status of publication. At the moment, one publication is currently being made, which is cloud-based web application with intelligent connected digital video recorder for Journal of Engineering, Science and Technology JSTEC. The review phase for the JSTEC journal is currently underway. The status of the thesis writing, currently drafting the introduction section of the thesis. This is the plan of this study for the next semester. First, we want to continue the development of proposed DRL and network model. Second, to continue on literature review paperworks. And last but not least, to start the data collection. That's all for me. Thank you.